Please start. Please introduce yourself. Please introduce yourself first. Maybe like 30 seconds, and then just get into the paper that you're talking about.
Okay, so hello everyone. My name is Manshu. I'm a pre-final year CS undergrad, and I'll be presenting. So this is going to be about this is two-part series, and it is titled Transformers to Mamba. And my part is about just giving a quick recap of Transformers. It will just be about 10 to 15 minutes of a recap, and I'll try my best to explain whatever the transformer is and how it works to the best of my knowledge. And I hope you're looking forward to it. Um, uh, Let me just share my screen. Okay, so I'm actually not permitted to share the screen from my iPad. There should be a user named Himanshu's iPad. Can you please grant the access?
Yep. Sure. 1 second.
Yeah.
I have made you as a host. Can you try now?
Uh, sure. Actually, I'll be, I'm sorry for the confusion, but I'll be presenting from my other account that I've joined from. It's Himanshu's iPad.
Okay.
So since you're the host, you can give Himanshu's iPad screen sharing capabilities or permissions, and then you should present from there.
So yeah.
So now I made Himanshu as a host, but I think, yeah, great.
So please let me know if my screen is visible.
I can see it.
Okay. So yeah, and so this is going to be, first of all, hello everyone. If you've joined just a minute or two late, I'm Himanshu, and I'll be presenting Transformers to Mamba. It is going to be a two-part series, of which part one is going to be presented today. And in my part, I'll be trying to give a very quick recap of Transformers to all of you guys, and not taking a lot of time of yours, just 15 to 20 minutes, and then we'll go to state space models, which will be presented by Madhav. So this is essentially what we will be discussing, and so we will get through basics of Transformers, the encoder and decoder stack, disadvantages of you know, some of the disadvantages that the deja vu paper talked about, some contextual sparsity and things like that. And then we'll get into SSMs and we'll eventually work our way up to Mamba. So let's start with a quick recap. And so this is the transformer architecture, this very complicated neural network architecture. This is the transformers architecture that was proposed in 2017 in the attention is all you need paper, which is just uh, you know talked about a lot in these days because it is just so monumental in today's world of NLP, and you can say AI in general. And so it is based on the idea of attention, and specifically multi-head attention, but we'll see what multi-head attention is actually composed of. And while it may talk about multi-head attention for the first time, the origin of attention was not actually this paper. And so as far back as I could track attention down, I found that the very first you know sequential, you can say, the implementation of attention or some sequential natural language processing task was done in neural machine translation in a 2014 paper by Bardenau, and they devised a mechanism called additive attention mechanism. And while this is not the scope of the paper, I would highly encourage you to go and read this paper. It is a very beautiful read, I would say, and be sure to check this out as well. So getting into what we're going to talk about. So first of all, before transformers, what was the landscape like? And if you've been working with deep learning, you imperatively have heard of RNNs, LSTMs, and GRUs. And so these were the benchmarks or sort of state-of-the-art approaches for sequence modeling tasks before the idea of transformer ever came about. But as with everything, these were somewhat ineffective at long-range dependency tasks. And so what long-range dependency tasks are, it's like there must be, in very simple words, a long-range dependency task is essentially, maybe you may have long ranges of data, and the data is just has to hold on to some of dependency onto each other. The components of data has to hold on to some what we can say relevancy with each other up to some very large uh, sequences. And so these methods were not as good for these tasks, as they maintain a lot of hidden states. Parallel computation was very difficult inside these RNNs, LSTMs, and GRUs, and so long ranges were not really easy to model using these methods. But that all changed with as transformers came along. So I hope I have given you enough motivation about the usage of transformers and why we needed transformers in the first place. So let's get a little bit into what the transformer is actually composed of. As we saw, it is a very complicated neural network architecture, which maybe, but it mostly consists of two stacks that are an encoder stack and a decoder stack. So the encoder is essentially, it is a stack. It is stacked model, and so in the paper, the authors, they use 6 identical layers of these encoders on top of each other, and in each encoder there are supposed to be 2 sublayers, and these 2 sublayers are your multi-head attention mechanism. We will take a look at what that is, and a point-wise feed-forward network. Now there are residual connections between these, and uh, which are then followed by some layer norm. And so this layer norm is supposed to be some, you just add the outputs that are coming, and then you just norm them. And I I hope you have an idea of what normalization and layer norm is. So I would like to get further. Then we come to the decoder stack, and uh, the decoder, as you can see, is just a little bit different from the encoder. There is another added component of masked multi-head attention, which is actually very, very important in case of the transformer, which we'll get to later. And other than that, we have just our plain old feed-forward network and multi-head attention. So after talking about this, let's first take a look at what basic self-attention is supposed to be. And before that, I would like to, you know, like give you an idea of what the encoder and the decoder are supposed to be. And so when you're giving this transformer architecture its own set of inputs, since these inputs are in sequences, and these sequence X bar may be composed of these tensors, these X1, X2, and up until some XT. What the encoder is supposed to do, as mentioned in the paper, it is supposed to convert them into some special representation, maybe some Z, Z1, or up to some ZT. And what the decoder in turn is supposed to do, it is going to take this representation, the decoder, and then it is going to generate your outputs one at a time. So I think I may have skipped this part while talking about the encoder and decoder stacks. And so this is what, if you couldn't get from the names, this is what the encoder and the decoder are supposed to do. Basically, this is what they're supposed to do. And so let's take a look at what basic self-attention is supposed to look like in the context of this paper. And so you have some inputs, which are just your sequence of tensors. And so these can be some x1 up to xt. And what you're going to get as an output are some tensors y1, y2, and yt. But the catch here is that each of the yi is supposed to be a weighted sum of the input sequence. And for now, let us assume that this is a weight, but it is not learned weight. We'll work our way up to how we're supposed to learn this representation and how we're going to define the three main notions of this, you know, this weight or this input sequence. So essentially what it is a function of some xi and some xg. These are your input tensors, and which is nothing but this. And we essentially then must sum them to 1. And for that, we use a softmax. So that is how we're supposed to get this parameter wij. Now, for us to make sense a bit more of what this input xi is supposed to be in terms of the paper and how it is used in 3 different notions, is that as you can is that in this way. The first notion that we're going to use it is as the query. The second one is supposed to be a key, and the third one is supposed to be the value. And what the key queries, the queries, keys, and the values are supposed to be a query. When we're talking about some input vector xi in the notion of a query, what it is supposed to be, it is supposed to be compared to every other vector, every other vector that is in the input sequence. And after that, using comparing it with every other vector, the attention weights are then calculated for its own input, which may be some yi. That is the notion of a query. What the key is, when xi is compared to every other vector to compute wij, which we've seen just here, wij for some yj, that is what we call the key. And what is the value? Value is being summed with other vectors to form the result of the attention weighted sum. And so this is the notion of the value. And so what these 3 things are coming from, where are these coming from? This is essentially your representation of input xi. And so we are using it in 3 different notions, which are queries and keys and values. That is how the basically the fundamental of what learned attention would be. Because as you can maybe guess from this representation, it is not supposed to be something that is going to be learned. It is a simple function, which if somewhat is defined like this. But if we want to, as we've talked about at the beginning, we must learn the attention for the long range dependency. So this is how separating it into 3 different notions, or these 3 different ideas, we are going to build up on how we are going to supposed to be learning attention. And so these 3 roles are then fulfilled as we're going to learn each query, key, and values. And now these are some new things, and these are essentially matrices. And these matrices are what going to give us the notion of the learned attention. This is how we're going to be learning our attention, these weighted matrices. And so what the new representation would sort of look like is for every qi, for every xi, the wij that we defined before just turns into this, and your wij essentially is the softmax of this wij dash. And so every output sequence that you're supposed to get then becomes this. And so now, as we were working upon this, we defined it to be a function of some inputs xi and xj. And then wij is going to be a softmax of essentially wij dash. And so how we've differentiated it from that to this notion is that now we are considering it to be supposedly solving us three problems. And so for that we have given it three notions: the notions of query, the key, and the value. And this is what essentially helps us learn attention. This is what helps us learn attention. And we then define each key, each query, each key, and each value like this. And this is how our representation of the wij dash, the intermediate between what you can say our output sequence and our inputs, is going to be. And so xi is supposed to give you these three things. Afterward, you're going to be calculating this intermediate, then you're going to take a softmax, and this is how essentially your outputs is going to be calculated. So let me not talk about this first. And so it was just a notion of how we went from assuming the wij to be a simple parameter to then attempting to understand how it is going to learn attention for long range dependency or any sort of language modeling task. So as the paper suggests, there's the main attention that is used, the main sort of attention that is used in the paper is the scaled output attention. So what is that exactly? And so as we've seen, an attention function is simply a mapping between the queries and the key value pairs. And so the output of the attention function is calculated as weighted sum of the values, with the weight assigned to the values is calculated by a compatibility function of the query with the corresponding key. And here I'm quoting the paper. Most of the text here is just quoting the paper. So whenever you read the paper, it just reminds of you, or reminds you of where you're supposed to do. And there's one difference here. The attention is just calculated as essentially this. And so this is the queries, as we've discussed. These are the keys, and these are the values. But here is something different. There's this parameter, this supposed scaling factor. And so why this scaling factor is used is because of the larger values of this decay. The softmax tends to just tend towards some very low gradients, and so this root over decay is provided as a scaling factor to counter that. After taking a look at this scaled output product attention, this is where we can successfully lead towards multi-head attention. And so as you may have noticed, we were just supposed to do a simple single scaled output retention while we were doing. And so what multi-head retention does is that it says that we can not only do that one particular we can not only perform that one attention, but rather if we linearly project h times with maybe different learned projections, it may allow, and in practice it works better because it allows the model to jointly attend to all the information from different representations of the subspaces at different positions. And according to the paper, this actually works pretty well in practice. And so That is why you do not see any scaled dot product attention here. You just see multi-head attention, right? And so in practice, this works pretty well. So that's why the multi-head attention is preferred. And so as you can see, the multi-head of QKV is you just concat for each representation up until H. And where each head I is just your simple attention calculated over for each I up until H. And so there were a few more things. There is a pointwise feed forward layer, as you might have seen this one. And so what this is, it consists of basically two linear transformations. And so first of all, this is supposed to be doing a redo in between those layers, and then a simple
Hey, Himanshu, there's
yeah.
someone who has a question. Maybe you can take a question before you proceed.
Oh yeah, sure.
Yeah, Venkat, you asked a question.
Yeah. Vector
I'm really sorry, but your voice
they
is
were
We
breaking a
can't
lot.
hear you, Venkat. Can you type your question in case your audio is a problem?
Hello, can you hear me?
Yeah.
Yeah, okay, now please, we can hear you.
Yeah, sure. Thank you so much. Could you please go to the place where you were showing the matrix multiplication, especially the dimensions of query key and values? I think 2 or 3 slides behind.
Here I suppose.
Well, no, 1 slide more behind, I guess. Where it showed Q is dk cross. The slide on my left, on your left. No, the next slide there.
Wait a second.
No, the slides were before this.
Okay.
Noticed one small confusion that I had with respect to the dimensions of the query vector. It showed it was cross dk. Should it be dq or dk? That is where I had a small doubt.
Okay, so which one? This one. Well, can you please
Down.
repeat once?
A little bit more down. I think 3 slides down.
Okay. This one?
Down, as in forward. 3 slides forward.
Okay, so 3 slides forward. Okay.
Slowly, could you please? Yeah.
This one?
One more. Just before this. Or if it's fine, can I point it to you accurately at the end of the thing? I don't want to take too much time right now.
Yeah, sure. That would be
I'm
fine as
sorry
well.
to interrupt. Can I speak?
Yeah, sure.
Himanshu? Yeah.
Sure.
So your question was like, why do we use particular set of dimension? If so, what set of dimensions I need to use? So if you look into the formula, you are like constrained with using same dimensions for Q, K, and V because you will be doing dot product in that. So on theory, you could like come upon with matrices which cancel out each other. But on practical note point of view, what we actually prefer is like keep all the dimensions of Q and V and K to be same and independent of each other. So 3 will be learnable. But if you look, I'll also come upon with the thing that with the use of single Q, you could have a multiple query at single query attention as well as group query attention program networks. So it's kind of a topic on its own, but yeah, on the practical point of view, the dimensions and everything are kind of same and independent of each other. Thank you.
Got it. Thank you so much. Thank you. Thank you for your time.
Yeah, I'm sorry, Manshu. Like, I think like we are taking too much time on transformers. Can you just wind it up a bit faster?
Okay, yeah, sure.
Thank you, bro. Yeah.
And so I hope I've covered up until multi-head attention, and everyone has a basic idea of what is actually happening. And so multi-head attention is nothing but it's just scale dot product attention over each linear projection, so that it helps to helps the model learn and jointly attend to all the information in with different representations. That is essentially what multi-head attention is. And before talking about positional encodings, I just wanted to or maybe we can talk about positional encodings first. And so as there are no recurrences or convolutions, it is very important that we provide the model with the notion of relative or absolute positioning of the tokens, how they're positioned. And so that is why the positional encodings are added to the model. And these are added whenever you are supposed to give an input to the encoder or the decoder, right? So if you could just take a look here, whenever you are giving an input, you're supposed to be providing a positional encoding so that the model has to, so the model can keep a track of what the relative positioning of each token is. And so it is happening at both the encoder and both the decoder, right? And so how it is formulated, it is supposed to look something like this, as it is mentioned in the paper. And so POS is supposed to be your position, and I is supposed to be the dimension. And these just form a geometric progression from 2 pi to 10,000 2 pi. Okay, and so that is essentially what the positional encodings, are for, to just to provide a relative positioning of the tokens. Yeah, and so there is still one thing that we haven't talked about, that is the masked multi-head attention. So why masked? So
Sorry, Himanshu. Can I just interrupt for a second?
yeah, sure.
I'm not like putting it down or something. On the position encoding, I just want to add this point too.
Yeah.
Instead of like using sine and cosine embeddings, like on the sine and cosine embeddings, you'll also get some meaningful extra information. But researchers also felt that this is kind of some kind of like restricting yourself into some kind of a predefined model. So what they did is like they also made these matrices to be learnable. So like instead of like using sine of position embedding divided by 10 power 4 whole to the power of some formulas, what they did is like they made they initialized an n cross n vectors where you'll have tokens of C and you'll have this tokens of n and you'll have this n cross n vectors and you'll add them both. So in such a way that n is also learnable. So this approach is keenly noted on vision transformers, BERT, as well as on many other cases, and many other cases in the sense like there is a lot of other models which were using it. And as per we see on 2024, the state of the art of a transformer consists of position embedding known as rotary position embedding. It comes upon with a rotation of some circle, I guess. I plan on covering position and embedding separately as one video, but the thing is like whatever position you're giving into the transformer model, that that also plays some kind of vital role into it, but not so vital as we speak. 2 to 3% of improvement is kind of like vital as we say, instead of using predetermined formula. Thank you.
Thank you, Madhav. And so moving on to what masked multi-head attention was supposed to be. And so why does this masked come from? And so when your model is supposed to be learning, you want it to learn from whatever inputs you have already given it, right? And so the future that it is supposed to, predict, it is supposed to be masked. Otherwise, it is like it is kind of like cheating. Whatever you're supposed to be predicting, you're just giving it already to the model, and that just doesn't make a lot of sense. And that is why we use masked multi-head attention. And so, moving on, I think I have briefly covered all of the points. Yes, and so moving
Okay.
forward,
Okay, you just covered this and we'll talk.
okay.
Yeah,
So
you sure you go.
yeah, and so as this paper Deja Vu suggests, there was always supposed to be some some limitations with the transformer models, and when this paper came out, Deja Vu, it talks about something called as contextual sparsity. And what the series of experiments the researchers were supposed to do was that they were trying to reduce the inference time in an LLM, and the one of the most natural approaches is either through sparsity or maybe through pruning. But uh, at the same time, the existing methods don't really help a lot, because usually you end up retraining the model, or you just forgo LLMs in context learning ability, or maybe even after doing all of this, the time or the speed up that you were expecting, it just isn't there. And so for this, the authors then hypothesize contextual sparsity. And what contextual sparsity is, it is essentially that the idea that there exists some input dependent sets of attention heads and multi-layer perceptron parameters which yield approximately the same output as the dense model for a given input. So what this is that there are some set of attention heads and MLP that maybe they could be anything in number, but what they found was that they approximately yield the same output as a dense model. And so as you can see, that they found out that there is approximately 85% of contextual sparsity for any given input.
Here, what does contextual sparsity relate to in the graph here, in the previous slide? Yeah.
So this one.
Yeah. Okay. Okay. So on the x-axis are the transformers layers, and the
Yeah.
y-axis is the okay. Okay. Got it. Thanks.
So yeah, this is essentially what it is. So each transformer layer, there is supposed to be some MLP heads and some attention layers, which are, which are supposed to provide outputs that are almost approximately equal to a whole model, right? And so this is what the idea was. They said that there is about 85% contextual sparsity, and so 85% of attention heads and your MLP heads, they just provide that same set of outputs that the whole model is supposed to provide.
Okay. And what is the theoretical reduction here on the second graph on the x-axis?
This so this is essentially your trade-off of accuracy.
Okay.
Okay. Yeah.
But in accuracy, I think so they are having a metric here with respect to how they represent it.
Yeah, so as you can see, there is some theoretical reduction, and so for that particular theoretical reduction, they're trying to sort of just see what that accuracy is supposed to be, and so for some static sparsity, for example, there is some maybe there is some set of MLP and attention head that is just static. The accuracy trade-off just goes from for this reduction, it just goes from there to there, right? And so for successive reduction, the contextual sparsity just holds up until this point, up until 8, in regards to what non-contextual and static sparsity holds on.
Mhm.
This is what.
Cool.
And so as we discussed, the natural, you know, the natural solutions to the problems were, only applicable to small scale models. The things like pruning or maybe sparsifying your models. And it is very challenging to find sparsity that will, preserve the in-context learning ability of the LLM. It doesn't harm how your LLM learns. And so I think that this is all for the recap. And I think we can now move forward to the state space models.
Okay.
Hey,
the-
before we go into state space models, I think we are already 40 minutes into the session. We have only 20 minutes left, and I think state space models will require quite a bit of time to get into. So, who's presenting state space model? Is it Madhav?
yeah.
Yeah, okay. So why don't you do one thing? Since we have only about 20 minutes and we should probably have about 5 minutes or 10 minutes for for Q&A. Why don't you spend, let's say, the next 15 minutes or remaining time to build a very strong intuition for these state space models, and then we can get into depth in another session or next week's session. How does that sound?
Yeah, it's really cool. Like I'll be most probably discussing the paper which I sent in the group as a
Yeah.
prerequisite.
Yes.
So I'll be discussing on that. That will take a considerable amount of time. And
Good.
what's the state of the art of state space model is. So
Okay.
that's the what I'm going to cover. So
Yes. Please build a very strong intuition, because that will make things very easy for everyone to understand.
yeah, sure.
Cool. Thanks.
So yeah, Prince, Himanshu, can I just share the screen, please?
Yeah. So you'll be sharing, or should I just
I'll be
move
sharing.
on to?
I'll be sharing.
Okay. Yeah.
Can I just get the rights to screen share, please?
So I think for that, Himanshu has to transfer to you because Himanshu is now the host.
Yeah. Just doing it right now.
Okay, I'll just give you some things which I will be saying in now. So the obvious question what we keep upon in this network is like, why do we still use transformers? The first thing. So that the thing which I keep on using transformer is like simpler math. Like it makes our life far more easier than is said. So even if I'm going with like older methodologies or doing even with going with older methodologies or tokenizing and everything, the game of NLP is like moreover simplified by the inception of transformers. First, we got like encoder decoder models. If you know, first we got a combination of encoder and a decoder model. Okay, give me a second. Okay, I hope everything is visible here. So first we got a combination of encoder and the decoder model. Encoder and decoder. And we have a now the NLP is like going towards only decoder model. So there'll be an obvious question like when should I use encoder model and encoder decoder model, and when should I use only decoder only models? So what they say is like if you know the conditional distribution on the data which you are modeling, like let it be text to image task or something like that, we prefer to go with encoder and decoder model. If you don't know about the distribution and you want to like some kind of approximate it like text to text or some other task, you only go with decoder model. So with that said, I'll step my foot on state space model. So state space model is more like observation thing. Observation in the sense I meant like you have to observe some kind of. Give me a minute. I hope this is visible.
Yes, it's visible, no problem.
Yeah. So state space model is more like observation kind of thing. You observe a particular state, like let it be Y, and let it be Y, and you kind of estimate that state Y with observed matrices or parameters which you have already. So if you look into this system, a pulley on a wheel system with a suspended mass T, you kind of like move into this direction U, and you have the spring constant. Spring is moving over opposite direction. As you move, it gives you an opposing force, and there will be some kind of friction, let's say, from it. So you don't have to like memorize this equation or something like that. The thing is like, first what you do to observe the state is like you first take the derivative of it. So x dot t is nothing but the derivative of x. And for the x2, you take a double derivative of xt. For the x2, you take derivative of x1 or the derivative of x, and you take an again derivative again. So you could kind of like notate it this way. So what do I like really mean in the situation? So with that x1 and x2, you kind of like make it into a linear algebraic form. So on the linear algebraic form, yeah, this step. So if you look into linear algebra form, you take x1, the derivative of the variable x, and x2, you have this thing, which is, let us say, some parameter a for the system, which we have discussed about. And the inputs are the, in this case, the recurrent connections, and another parameter b, and what you are having an input as u. So you estimate an x dash to be a parameter of ax plus bu. So that's the starting point of all SSMs. And if you go on, you kind of like estimate the x, which is coming from here, to be c times x and d times u. On the paper, like until up to Mamba, S4s and S5s assumed d equal to 0. So y is equal to some kind of k times u, which is nothing but k times x to make it. So I forgot the to make it continuous. What I'm saying is, it has some factor k times x, which is nothing but a control factor which we say. But the thing, instead of like dumping you with all the formulas which I have, the simpler way to analyze it, I could say this as some kind of augmented matrix, like x to be some kind of augmented matrix of a and b, which is into x and u. So this is kind of a gated function, or some kind of like in the terms of LSTM, what you'll say is like with the hidden layer and with the input layer, and you could say this thing as output gate, talking on LSTM terms. Because when you could kind of like accelerate on state space models, you could also accelerate on LSTM, which would be like, I won't be covering, but it has recently come came towards this thing on the recurrent connection. So there is like okay, I'll just look at this. Okay, so on the S4, what they did is like the parameters of A are initialized as hypomatrix, and which is defined by this equation. The parameters of A, like the x dash A times x plus B times U. So U being a input function, input in the sense what we have, and x being the whatever you're getting at the current time step. And so you could also recurrently write it as xk plus 1 is equal to a into xk minus 1 of the time step before and bu. So it gives you like two options with it. So you could also say that why can't I like for the x1 state I could have b of u naught, and you could stack upon these matrices a of x naught plus b of u1, and you could just stack upon these matrices and just say that you could also apply a convolution operation. You could also do that, but the thing is like on practice this convolution operation haven't like given stability as we say, but it also like overcome in the Haina convolutions paper, which we'll discuss on the next part of the series. But this is the thing. So you could either compute it recurrently, the S4 given you then freedom of computing on the state space model space recurrently, or using convolutions. So yeah, so I have an A, I have an B, I have an B is a C and D. B in this case is like NN dot parameter with gradient descent, and A is like explicitly mentioned as an hypomatrix, and C is also NN dot parameter with the gradient descent, so there is no issue with that. So can I just use this thing directly? Like, can I just have an A? Why don't I like plug it in the value of A and get something useful? So turns out you can't do that. If you do that thing, the problem will be you need to have an expensive computation thing, because the input functions which we are giving are assumed to be continuous in the case. So we have to discretize with the step size of delta. And while discretizing, it's up to our choice what to do. So while discretizing, we convert this continuous function into group of discrete functions, and we also make discrete like variables over here. So you apply here bilinear transformation. In the paper, they told that zero order old methods. So you apply a bilinear transformation, or on the case of S5, they just exponentiated the parameter with A with delta. So you don't have to like remember everything of it. So on the typical state space network point of view on the modern scale, first you need to initialize A, B, C, and D on the continuous space, and then discretize with parameter delta, and then with that you could compute A delta, B delta, C delta, and D delta by either your means of error function, like you'll be using error function to update these values, and UK being the normal input function and XA being the recurrent sequence of it. So that's pretty much it. If you look into really high point of, if you're really looking in the high point, I'm just sorry. If you're just really looking on a high level, this is just state space model. So on the S5, they used different methodologies, and Mamba, they use different methodologies. So this is the foundation of state space models. So I'll just encourage everyone to, like, if you have any doubts in this, please let me know.
This is cool. So could you show it in the paper, which system of equations that you referred to? I I mean, so you are deriving it from the first principles here, which I
Like this
really
is
like. Yeah.
no. In the paper, they just mentioned up to this thing. This I just took from a classical.
Okay. Got it.
This
Thank you.
thing, like I just made for the case, which is like interpretable. Like if you just directly go into state space model with these parameters, like it will be confusing, right? So
Okay.
I just wrote this thing to give some idea how this thing would be. So how could you observe a particular variable on the space by using this? So, but you can't apply this directly on machine learning, which they said on the paper. So I'll just give the end notes if there is no doubt. Like if you're having doubt, please let me know. Like I'll just complete it and give end notes on this paper, because that's kind of influential, and that's what craze of Mamba and everything started. So like,
Could you
yeah,
also tell us a bit about the Hippo matrix, the origin of that, since I am not familiar with that kind of matrices here.
okay. So Hippo matrix, okay. Instead of me writing, I could just show the. Give me a minute. The Hippo matrix have been visualized in the appendix of the. Yeah, I hope you could see it.
Okay.
So this will be more kind of this. In this paper, they also made it like if these parameters are diagonalizable, then it will be more easier to multiply it directly rather than using NN dot parameters or something like that. So they focus the entire paper in diagonalizing more than doing this thing. They focus more on diagonalizing rather than um, focusing on the state space part itself. I'm not making them like saying this inferior thing. It is really really influential thing on the state space thing, state space model, because this is what I say is like inception of the Mamba or Vision Mamba as we speak. So in this section, like they were really restrictive on diagonalizing A, B, and C matrix. So why I'm saying is like because on the later section there will be some relaxation over these part, but you have to kind of remember that A is restricted for now. You have a predetermined matrix, and B is like some kind of diagonalizable matrix with the parameter, and C is also some kind of diagonalizable matrix with the parameter. So as session goes on, we'll see a relaxation over these periods. So yeah, so I'll also come upon with this thing. Sorry, um, this thing, the matrix which you are multiplying, and if you just not try to diagonalize it, I'm trying to say in the context of S4, if you're not diagonalizing this matrix, you'll come upon with computing too much big matrix into input and recurrent function. But the thing in Mamba, what they did is like they kind of converted into putting this matrix when you are not multiplying or not doing anything. You just have this matrix in HRAM, and when you are doing multiplication or some kind of sort, you will multiply in the memory of SRAM. So SRAM is like really short buffer but really high throughput. SRAM is like really large buffer but small throughput, like moreover cache versus RAM in the case of CPU. So that's it.
Cool. Thanks.
So I think like, does anyone have any doubts, or like, if you don't get clear on one part, like I'll be more than happy to do it.
Hey, no, this was very fairly comprehensive, and I think deriving from first principles was a very good start. Kind of gives you a very good starting point to start thinking about the next steps. And I think the rest of the paper will naturally follow. So yeah, I wanted to thank you for that. We
Yeah,
have about 3 minutes left, so if
yeah,
we
I'll give
don't have
you
any
a
questions, yeah, if does anyone else have any questions? If not, what we'll do is we'll finish the session today and we'll continue exactly a week later. And in the
I had
meanwhile,
one question.
yes, yes, yes,
Is
please.
it okay? So maybe this is a general question also. Maybe what is the best way to learn attention? Maybe obviously there are resources like Karpati and stuff like that. But any recommendations from anyone? I want to know underrated resources as well to
like,
understand transformers in detail.
sir, like you
Annotated
have to.
transformer is probably one of the best places that you can get to understand transformers. I mean, that was one of the resources that I'd used in the past. But I mean, I think I learned most of it just by reading the transformers paper repeatedly. But yeah, I mean, if you want a quick distilled version, then or like a very detailed version, then yes, annotated transformer helps.
Thank you.
Like I also go with the Raj sir point of view. Like, in the vanilla paper, you'll be coming into a phenomenon called cross attention. If you're like going into paper like in depth, you'll kind of know that. But
Hmm. Yeah.
if you're like me, like, you're just looking into online without reading paper, so you'll just come upon confusing terms within this. So what I actually say is like read from the paper. So that's the best resource you get. It ain't much also complicated on the first stage. Like, they initialize encoder decoder model for translation tasks. So yeah,
Thank you.
So
Thank you
I
both.
had a small question, if that's okay.
yeah.
But this is not regarding state space models, regarding the positional encoding, the sinusoidal embedding formula that someone spoke about.
Yes,
I
sir.
think Himanshu Bhai spoke about.
Yeah,
Could I ask that?
yeah, sure.
Okay, so the logic behind positional embeddings was to not penalize and somehow capture the context between far off words. That's why we introduced the notion of a sinusoidal embedding. Am I
Yeah,
right?
yeah,
Okay,
kind of, yeah. But
okay,
the thing is like, give me a minute. So if you
sure.
look into sinusoidal embedding, on the sine case, you will have something like here, and on the cos case, you will have something like here. This on odd positions and this on even
Right,
position.
right.
So the thing is, uh, you kind of like say, or some kind of categorize it like this is start to end and this is start to end from the odd to even position. But the thing which I said is like, this is kind of like enforcing, or this is kind of like restricting the network to believe this is the absolute position of something. So
Mm-hmm.
if you look into BERT or something else, you just initialize a randomly initialized weight matrix, which would apply a weightage between whatever sequence it's coming, 1, 2, or 3. So instead of making this enforceable,
Uh-huh.
researchers found more intuitive and better performance when they are making it learnable. So this is kind of an old. So you will have rotary embedding.
Encoded. Okay, embedded. My question exactly was when you aim to not penalize distance in the embedding, the very nature of the sine curve itself causes you to favor some kind of positions over the curve. Let's say you're talking I equal to 4 and 7. Let's say they fall on either sides of the maxima. The
Hmm.
delta of those I is 3. And let's say 7 and 10 fall on the both fall on the right side of the minima of the maxima, and their delta is also 3. But then on the y-axis, their delta will be much greater for 7 and 10 than 4 and 7. So in a way, aren't you still penalizing in sinusoidal embedding, or is that what you're referring to when
I
you said
don't I don't actually mean that, because
okay?
on the inference part, I'll just write you some kind of algorithm. You have this part on odd and even. So speaking on tensor point of view, you'll just add this thing odd and even. So if you're taking gradient of it, this will eventually go to 0 and you will have a gradient which is dependent upon the input position of x. So long story short, you won't be penalizing over the position encodings, just the input of it.
Okay, got it. Thank you so much.
Yeah. So I'll give the end notes of it, since there is no more questions. The thing we go upon with SSMs on the S4 paper, they have said some kind of like transformer really fails on long range attentive tasks. So on the long range task, what they said is on path X dataset, like you determine the path of where it is going with that. So on the path X dataset, transformers like really perform poorly on like around like 42% of it, like 42% is really smaller than uniform distribution being just random guessing. So 42% is like really worse than guessing. So this is what made the kickback of recurrent neural networks, so that we will have some context on really large data. So that's why the state space model have been introduced, and state space model have been like some kind of polynomial. Yeah, kind of like polynomial, but not like really larger than quadratic as time complexity in attention. So you have this cheaper compute, more expressible way of understanding the data, and you could do long modeling. So that's what state space model defines what it is. So with that, I kind of conclude the session, and we'll go upon with part 2 and part 3 of it, like the convolution side of SSM. I'm really excited to do it. Thank you.
Cool. Thank you, Madhav and Himanshu, for this session. I originally wondered why we started with the basics of transformer, but I see that it was necessary for this session to make sense. So thanks to the two of you for doing this. So we'll continue next week on part 2 of state space models, and Madhav and Himanshu, we are looking forward to the second session. Please share all of your notes and your documents in the group, and the video recording as well, and I'll put it up on YouTube.
Yes, sir.
Okay.
I
Okay, then
think
thank you so much,
Curians,
and have a nice evening.
yes, sir. Thank you.
Thank you so much.
Bye-bye.
Thank you so much,
Thanks,
everyone.
Himanshu. Thanks, Madhav.
Yeah,
Thanks,
thank you.
guys. Take care.
I want to thank Himanshu. Without him, like I couldn't make the half of the lectures. So thank you, Himanshu.
Thank you,
It's a-
everyone.
It's a pleasure working with you.
Yeah, thank you, bro.
Mother, can you exit the meeting? Actually,
Yes,
then
yes,
yeah,
sir. Yes, sir.
end for everything, please. Yeah, thank you.
Yes, sir. Can I just end for
Yeah,
everyone?
exit, end for all, end for all. That's all.
Okay,
Thank
sir.
you.
Then you'll get the recording, right, sir?
Yep, I will
Yes,
get
sir.
it.
Yes, sir.
Thank you.
Thank you, sir.